Good morning, everybody. Welcome to CDS. I have the honor of giving these introductory remarks here and trying to get everyone super excited for today's content. There are a number of workshops going around the side on some really interesting topics, and there's a whole bunch of very fascinating conversations going to happen up here on stage. My pleasure for the next 45 minutes is to try and give you my prognostications for the next 3 to 5 years. So, as we start this, let's define the future as being 3 to 5, so between a World Cup and an Olympics. And the context is going to be global, and we're really going to focus on OTT, which is hopefully why everyone's here. If you're not here for over-the-top video, you're probably at the wrong conference. So let's start right off with my favorite topic, which is streaming formats and latencies. This slide you've probably seen in a bunch of different guises before. This one's been recycled many times. I would like to start with across the top and explain what I consider long latency, regular latency, and then ultra-low latency and real-time. So we'll put this in context of business use cases, because I think that's the best way to think about this. So let's start with the use cases. So we've got live sports and esports, which are the things that really demand real-time video, demand something that's going to be interacted with and watched in an interactive way. Then we have new things that we're doing online, like gambling. Now it's been the federal, at least in the US, it's now it's up to the states to have their own regulations. I expect to see an explosion in this space. We have live auctions going on. We have these trivia games, which are very popular and all over the place and in lots of different formats. And of course, we have voice and anything that needs real-time interactivity. These all fall into what we call the ultra-low latency or the real-time world. So anything under 4 seconds or under a second. That's how I define ultra-low latency and real-time. So where is broadcast today? Traditional broadcast systems, so direct-to-home, cable, IPTV systems, typically, depending on whether you're in Europe, down near the 4 seconds, or whether you're here in North America, more like 10. If you're on a direct-to-home, maybe up in the 14-second type territory. But within that bracket, layer on how people watch sports today, how they watch an event, a big game, that very large football-based event that happens sometime in February. They watch it and they talk to each other through Twitter. They talk to each other through text messages, through WhatsApps, TikToks, or whatever my children are into these days. I'm not quite sure, but there's always another word that they're saying which I have to then go and research and make sure they're not doing something that I don't want them to do. So people interact with it. So they need to be within a certain latency window. The problem we've had with ABR, and this is a common problem, we all know about this one, is when you have larger segment sizes, the way we adapted video to work on the internet was to not try and make video go through the internet, was to change video into files, which the internet serves really well. But we put them into rather long segments because we had trouble getting them through the internet to start with. We've been reducing the segment sizes, trying to get ourselves closer to that broadcast latency. So we've gone from 6-second segments to 4-second segments. Now, a lot of people are using 2-second segments, and some people are even trying 1-second segments. All of us trying to grab ourselves down to that latency. My first prediction is going to be around chunked CMAF, which is not new, but it's just a new way of using two existing tools. So not only the chunked nature, the ability to chunk encode video, but also chunk transfer video through the internet, which would give us the ability to hit not only the traditional kind of latency ranges where maybe we have content we don't care so much about the latency. It doesn't have to be like 10 seconds tight. It can be all the way from 30 seconds down to 1 second is achievable today. We've done that with this technology. It's much more comfortable in the 2 to 3 second territory, gives us a little bit of headroom, some buffering. And then right down in the bottom corner, if you have to do real time, I firmly believe Webrtc is the right format. It's designed to do that. It has a different profile, but it requires a different network. All of the things in orange there can be deployed over existing CDNs and are supported today by browsers and players and all of the frameworks that we need to make it work. So I'm going to zoom in on this territory, and we're going to talk a little bit about CMAF for the next piece. So these slides, full credit to Phoenix, who did this research. Phoenix is a Webrtc company. They did an event during the last big football event where they looked at, they had somebody in the stadium, and then they had crowdsourced a bunch of people watching the apps on different platforms. And they tried to work out what the offset between the game on the field and all of the different apps were. And as we see from CBS, who are probably running a 4-second, down to Yahoo, who are probably running a 6 to 10-second, we have the typical range of ABR latencies we see in the wild today, which is from 30 seconds up to about 45. What was more surprising, and something that we've kind of known about but haven't really quantified, or I haven't seen a good slide on this, is the drift. So because the way ABR works is, if you can't show the frame of video, you wait, you pause, you rebuffer, and then you catch up. What tends to happen, especially if you have any kind of DAI or any other kind of platform that's interacting with that, every time you cut away and cut back, you slip some time. Some time gets lost in the mix. So by the end of the game, we found that people were almost 2 seconds disjointed, or within that range. If they'd restarted, they obviously would have jumped back. But the player itself has drifted over time. So what you end up with is your audience spread over 2 to 3 seconds, 2 to 3 minutes of time, which breaks the interactivity. The spoiler effect is gonna be huge. I did not watch Game of Thrones last night. I don't think it was probably as spectacular as last weekend's. I don't think there's anything that I need to know yet, but I still don't want to know. But that's why I've been staying away from my emails. I'm sure there was something exciting, but I didn't watch it because I had got a good night's sleep, so I'd be ready for this presentation. I will be watching it later. But you see, the audience gets fragmented. So how can we address this? Well, one thing is reducing the latency. The other is reducing the drift. So let's talk about the latency. CMAF has a couple of interesting features in it, and I firmly believe CMAF will be the core foundation format going forward. What CMAF allows you to do is, if you look at the structure here, for those at the back, this is going to be fairly hard to see because they're kind of small text, but you have a header and a block of data. So let's take that top line there. Say that's 6 seconds worth of data. What happens is the encoder waits until it has the whole 6 seconds before it transmits it. So it's encoding video, iframes, pframes, vframes, lovely, 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 putting them into the MDAT. But it waits until it has the whole 6 seconds before it says, hey, here's a new file, and it sends it to the CDN. The CDN then sends it along to the player. The player then stores up 3 or 4 of these, and then it starts actually playing. So the encoder, if I have a 6-second segment, the encoder holds on for 6 seconds. I'm already 6 seconds behind before I've even started. I'm already at the typical broadcast latency. The nice artifact of CMAF is the ability to put headers in much more frequently. So I can break up that big 6-second block of data. This is still one 6-second file, but I've put extra headers in the middle so I can transmit these bits of data. And they have meaning to the decoder earlier. So what I've done here is every 4 blocks of data, I'm sending it. So say that's 100 milliseconds. Now I've sent that data through the network. So if you're at MUX, or you saw me speak here back in November, you'll have seen this lovely analogy before. So this is the analogy for chunk transfer using buckets of water and monkeys. Some people haven't seen this one already. That's excellent, right. So the faucet is the video encoder spilling out video bits. The first bucket is the encoder. So the first bucket has to fill up with 6 seconds worth of video before it then gets transferred to the CDN. That's the middle bucket. Once the CDN has it, it passes the bucket on fairly quickly to the decoder. The decoder, actually, there really should be 3 buckets here, because most HLS players today will wait till they have at least 3 buckets worth, 3 segments worth. And that's where the majority of the delay comes in. So reducing segment size reduces how quickly the buckets get handed on. But it also causes a lot of thrash in the network. There's a nice feature in HTTP called chunk transfer. So I've chunked encoded, and there's also a thing called chunk transfer. So this gets very confusing. So I have double chunking, 2 chunks. Chunk encoding, chunk transfer. Let's keep those 2 separate. Chunk transfer allows me to request a file before it's finished writing. So this is the analogy. If I take the same 3 buckets, and I get myself a drill, and I pop a hole in the bottom of all the buckets, now when the video goes into the first bucket, that first 100 milliseconds can transfer immediately to the CDN, and then it can transfer immediately to the decoder. Now, on the decoder side, I have 2 choices. I can use that extra, the fact that I've got the data earlier, to just build a bigger buffer, which gives me more protection. Because the only place the buffer is actually useful in OTT is at the decoder, where it has value. Having buffer in the CDN, completely useless. Having buffer in the encoder, completely useless. Where is it useful? In the decoder. If we build up the buffer, so we have, say, a 30-second buffer, we've now gained ourselves 6 seconds of extra protection that we didn't have before, just by switching to using chunked encoding, chunk transfer versus traditional. Or, and this is how we get to low latency, I can decide to change my player behavior and say, you know what, I want to run right on the bleeding edge. Make my buffer an arbitrary size. Don't wait for a whole segment. Let me think about this as what it is, which is really just a stream of bits. So we've gone from using files to navigate video through the internet. back to a stream of files. So we look like stream video again. If we do it over UDP, guess what? We're right back to some stuff we did 20 years ago. But within a standard framework that's compatible with the CDNs we've deployed today. What does this look like from an architecture? So the first mile, you have to have an encoder that's capable of doing this. Good news is, a lot of commercial encoders today already have this mode in there. They actually had it in there for a long time to do traffic smoothing. What we've done recently is updated the code where they actually allow the bits to be pushed earlier as well. So it's a reorganization inside the encoder, but it's not a huge change. And what's nice about the network is it doesn't cost any more to do this. It's the same number of bits. In fact, the traffic pattern's a lot smoother and a lot cleaner for the network, so it's actually nicer to the network. You need a live origin that can accept chunk transfer. Most live origins now can accept chunk transfer bits. You need a distribution network that can then also support what we call a chunked request. So we use HTTP 1.1 posts to get the data from the encoder to the live origin, and then we use HTTP 1.1 gets with a chunked header to request it from the edge. And what happens is we set up simply a chain where the player is requesting a 6-second file. As the encoder's making it, the bits are being transferred and passed all the way down the chain. So we've set up an end-to-end flow. But it's a single file request. So it's very nice on the operations of the network. Is HTTP 1.1 chunk transfer the only way to do this? No. You can chain together WebSockets. You can chain together HTTP server pushes. But these two are not currently supported by most of the major networks. HTTP 1.1 chunk transfer has been supported for quite a long time now. So the encoders can do it, the players can handle it, and the network can handle it. So what are we waiting for? The good news is, not a lot. We have customers doing this today. There are a number of commercial offerings. There are a number of open source offerings, both on the encoder and on the player. And there are a number of CDNs, including ours, that do support this end-to-end. And with this, we've shown very stable latency in the 2 to 3 second territory. The demonstration down in the bottom screen, if you missed it at NAB, for shame for not coming by and seeing all my hard work, but we have two demonstrations. One, we had the dash CMAF on the right-hand side there. We also had a low latency HLS. I do caveat with until June 3rd, we won't know exactly how Apple was going to specify this. So this was the FOMS Alliance group of people that came up with a way of doing it using these prefetch tags, which basically give us ability to hint the next name of the segment, because HLS, we don't know what the name's going to be until we see the next manifest. But we had both LHS, at least a prototype of it, and -CMAF running on two separate players. That was a JW HLS-AS Akamai demo on that side, and this was a pure -JS demo on this side. But both within 3 seconds, both within a frame or two of each other in video, because they're both using the same kind of technique, but they're both using the same byte stream behind this, the same MP4 fragments. So my first projection, over the next 3 to 5 years, live latency will shift from where we are in the 45 to 30 second territory into the 1 to 10 second. I believe we have the protocols, and we have the tools, and we have deployments of it now where we can have the latency be determined by the application, not by the technology. In the past, we've been driven by the technology, but I think we will be able to select it now to match what we need for our application. Synchronization. This is great, the drift problem. How can we keep the players from wandering away from each other? ABR players today fundamentally work on the I will show every frame of video modus at the frame rate I receive them, which is I will wait if I'm missing something and I'll catch up. That makes sense, because if I'm watching an episode, I don't want to see, whatever happened last night, the critical moment where somebody comes down with the sword and then it cuts and comes back and then, oh, what happened? Or somebody kicks the ball and, oh, look, the score went up by 7 points. Oh, how do we, what happened? We missed the action. ABR worked on the principle of I'm going to keep the bits in the buffer, and if I don't have enough buffer to play, I'm going to wait until the buffer's full again, so I show every frame of video. Traditional TV doesn't work that way. Satellite doesn't work that way. Webrtc doesn't work that way, which is if the frame of video doesn't arrive within the time it has to be shown, because it's end-to-end synchronous, you just don't see it. So there are a couple of ways we can solve this. I'm going to show you one way that we've done already, and there's another way we can do this, which is you can achieve synchronization today with players by just having a simple external time source, say an NTP server, an ability in the player to change the playback rate very subtly or very aggressively, or just skip, and a common latency target. If you put those all together, you can achieve synchronization. What I have here is 3 players. One's on Android, 2 are on Mac. All of these are synchronized within a frame of video of each other. There's nothing magic about it. These are standard -JS players, where there's a little bit of JavaScript on top, which tells it what latency target, what do I want the stream latency to be. It's looking at time.akamai.com to find a common clock reference, and it's then comparing the timestamp in the player to the timestamp from the clock, and it's putting those together to work out, do I adjust the playback rate to make it go faster or go slower so that my videos all synchronize? And you can be as aggressive as you want, or as subtle as you want to bring these players together. But it is possible to get 3 completely separate devices on 3 totally different networks within a frame of video without any other special protocols, just standard player and a common time source. So my second prediction is that live OTT services will be synchronized within a second of each other. It's very easy to do. So you'll notice the big transition means I'm changing topics wildly. So as it pivots around like that, the slide transition, I will change topics quite a lot. So this is based on a paper that was put out by Jeff Hudson last year, where he's talking about the change in the structure of the internet and what that implies for us as OTT providers. So let's go back to the 1990s. Ooh, and let's not exit the slideshow. That little blank, that blanks the screen. I forget it does that. Before CDNs, a client wanting content would go all the way back to the servers and would go and get the data. It would then go across the transit network as we know it today, through the ISP to the consumer. This became problematic. It was hard to scale. It was very hard to service clients at the edge. So end of the 90s, what happened? 23 years ago. CDNs arose. CDNs were placed at the edge to basically act as caches so that once content had been retrieved once, we could then serve it again without having to traverse the whole transit network. This offloaded the cost of the transit network, this offloaded the amount of data, and it improved the performance for the customers. CDN did such a good job of this and made so many media companies so successful. The really biggest media companies figured this was a really good idea, so they all started doing exactly the same thing. Oh, here comes the request for a local cache. So the big media companies wanting to have the same performance and wanting to have their services have the best response at the edge also have started building caches at the ISP. Furthermore, what's happened over the last 5 years is they're direct connecting those caches back to their data centers. They're basically going around the transit networks. They're building a plethora of overlay networks. What does this mean? This means that the nature of the internet as we built it is not a generic open platform of switch network. It's a series of very big media overlay networks feeding the edge caches of the biggest media and the biggest CDN providers. So what does this mean? I think death may be a slightly hyperbole term, which was a good eye catch. If you've not read this piece, it's really worth reading. But it did catch my eye and made me read it. What it means is, from a regulatory and from an actual implementation standpoint, we are going to have a different internet than we started out with. It's not going to be the same model which some of the rules have been written for and the designs have been built for. It's going to be a network of very high-powered cache servers serving the majority of OTT traffic right from the edge, fed directly from core data centers. So my third prediction, is that the majority of video traffic will be served from those edge servers, and the majority of those will be fed from directly connected networks. So, anyone agree with this headline? Yes, a couple of hands up, excellent. So, I went through this with 4K, but 8K is even worse. But I'm going to sit that close to it because I want to see the pixels. This is actually a fake headline. Jeffrey Morrison did not write this piece on CNET. However, 7 years ago, he did write this piece. 7 years ago, we were having the big debate. Now, I've worked in video encoding for 20 years. I know how far I have to sit and optical acuities, and I can do basic trigonometry, and I understand that. But I really do like my 4K television, and I do like HDR, and I do like all the cool things that came with it. But 7 years ago, we were saying 4K is stupid. Nobody's going to watch it. Nobody's going to produce in it. There's only so much glass, and there's only so much light in the universe, and all the physical requirements. But it didn't matter. The CE industry, which even if you're in the first row, this is definitely going to be an eye chart test for you here. The graph shows that 4K TV sales are going up and to the right. And the majority of sets, any panel over 55 inches is 4K, whether it's being driven that way or not. They're just making the glass that way. So 4K, whether we wanted it or not 7 years ago, happened. I believe the same thing will be the industry will be driven the same way for 8K, mainly because the TV manufacturers want us to buy more TVs at the same rate that we replace our other consumer electronics. Waiting a decade to replace your TV? Oh, no, with smart TVs particularly, you're going to be wanting the next processor. It's going to be like buying a laptop. So you're going to get an 8K panel whether you want one or not. And so if we're going to have to deliver 8K, what does that mean for us as OTT providers? Well, first of all, let's ask the bandwidth question. So 4K today, which we deliver using HEVC, is around 16 meg. So worst case math, that would be 64. Now we know that the way that HEVC was written is it actually was designed to handle 8K. We thought about this, so we came up with these things called coding tree units, which are scalable and elastic, so we know it's going to be more efficient at 8K. Also, we have two new codecs coming down the pipe. We have AV1 and VVC, VVC Virtual Video Codec, which is the next MPEG iteration of HEVC, are going to be at least 20%. VVC is aiming to be at least 50%, but it's somewhere around 30 today. AV1's about on par with HEVC, but it's got more tools coming. So we know it's going to be better. So in 3 to 5 years, I expect these things to work out. And so we should be realistically somewhere between 40 to 50, probably on the lower end of that scale for 8K. So 40 megabits per second. Can I deliver that to a house? Well, good news is today, even in China, we could do that. There's enough bandwidth in the kind of the average mean fixed speed. Some markets, maybe not. Some for mobile would be challenging. But 40 meg is totally doable. And in 3 to 5 years, given how fast bandwidths have grown, I think we should be in good shape. So I think we can deliver 8K when we get there. And so this brings me to my fourth prediction, which is 8K content will form the top bit rate of the ladder right around the World Cup in 2020. And given that Blackmagic now does a nice video switcher, complete ATEM for like 10 grand, I think it's within the realm of possibility that we're going to start producing in this as well. But again, we're going to get into glass and light and all that stuff. So talking about advanced formats, let's talk about HDR. Now, this is only 2 years ago, this starting slide. This was the ecosystem. Now, full credit to Yuri, these are his charts. I'm just presenting them here. So this is the state of the universe. We had 4 standards kind of competing. HDR10 at least formed the backbone. Everyone supports HDR10. And then there are the 2 metadata, the dynamic metadata fiefdoms of HDR10 and Dolby Vision. And then we have HLG as a backwardly compatible, useful for live type productions. So over time, the ecosystem has grown. More people have come in. This is October. So this is just 6 months after the first one. Spin forward to the beginning of last year. In comes Philips Technicolor with another one on top. What happens right around the middle of the IBC is we start to get some standard numbers in here, which is good, because now at least everyone knows what the framework should be. But as you see, the bubble starts getting bigger and bigger. Everyone still supports the baseline. But definitely you see that there's kind of a separation, and Dolby Vision is definitely the more dominant one for dynamic. Spin forward to the beginning of the year today. This year, becomes a bit of an eye chart, because I had to split this up into, they had to start splitting these slides up into TVs, into devices, and into streaming services, because the chart was just getting too unwieldy. So what's not happening is there isn't like none of them have gone away. In fact, we're just adding more. And given that for static metadata, it's just another lookup table and another kind of function, which can be downloaded or updated into these devices, which are basically now computers with panels or computers on sticks or in boxes. It's conceivable that we don't have to converge some of these things. So my prediction is devices will continue to support multiple HDRs, especially where it's just if it's static metadata. I think Dolby right now is carving out quite a lead on dynamic metadata, and I think it will continue to maintain that. But I think HLG, given that it's backwardly compatible and it's much easier to live produce, will be the format that we're going to use for live sports and live events. Quick, not so fast. So pivot over to protocols. Quick unicast, UDP internet connections. Quick has been around for a while. Quick is now deployed on all Chromium devices. Quick is used extensively by Google and Facebook and by others to accelerate web traffic. Quick versus standard HTTP1 gives about a 22% improvement. Quick's real benefit, because it's not bound by round trip and not bound by standard congestion controls techniques, the longer your round trip, the bigger the benefit. So if you're at a round trip time of 50 milliseconds, that benefit goes from 22 to 26%. Versus HTTP2, there's about a 15%, because obviously with HTTP you've got bundling and there's some other cool stuff going on in there. Again, on the longer RTTs, because even HTTP2 is still ACK bound, and you have to do the throughway acknowledge, it's still, and you have to do the extra step for setting up of secure connections. It does give you an improvement on those longer round trip times. So over 50 milliseconds, again, about a 25% improvement. Now, there are a lot of different protocols out there. There are a lot of different protocols we can choose from. This chart here, which I don't know if black and red were the best two colors to pick to show on a projector at this distance, but I'll talk you through it quickly, which is, everyone says, oh, I've got this great new protocol. Yeah, use BBR, bandwidth bottleneck and round trip. It's so much better than fast TCP, or it's so much better than Reno, or it's so much better than Vegas, or whatever the TCP algorithm you're using. The problem is, some algorithms are really, really good. Some algorithms are too good. So if we just use the one that we thought was the best all the time, we would blow out all the other traffic on the internet to your device. Our service would be great, but everyone else's would be pushed aside. So you have to be careful which protocol you use at which time, and only use the right one at the right time. Otherwise, there's a lot of unintended consequences. So as an example, what I have here is, on the graph, we have BBR, so bandwidth bottleneck, and round trip, and then we have fast TCP. The black line is a background download going on, and then the red one, every 1 second we pulse a download, simulating, say, a media segment download. So say this is a 2-second segment, and then for one second we're downloading. What happens is, when BBR fires up on the same link, the fast TCP connection is completely obliterated. Its windows collapse. You can't get any transit through because basically it's the congestion algorithm says, there's too much traffic in the buffer, I've got to back off. BBR's like, hey, the buffer's open, I'm going for it. And so it completely dominates that connection. Even when BBR backs off, fast TCP can't recover enough to try and make up the ground. It's basically, its window's only slowly opening again. And that's part of the problem with these different congestion control algorithms. So what would be better is if we could dynamically select protocols for the connection based on the conditions at the time. So one of the things, there's a lot of research going on right now, a lot of research we're doing, a lot of other peers in the industry are doing, is trying to, on a per connection basis, pick the right congestion control algorithm or the right underlying protocol technology for that moment. Trying to pick the one that's the right one at that time. Be it quick, BBR, Reno, fast, cubic, or just simply packet pacing. We have a lot of input variables. We know a lot about each connection. We can make a decision that says, hey, given the current RTT we're seeing, given the current packet loss on this link, given what else is going on this link right now, what we know about it, we can make an intelligent decision, or at least we can provide those variables to feed into a machine learning algorithm and let it make the decision. And our initial results are saying, using machine learning to provide dynamic path optimization is going to lead to better protocol optimization on specific links at specific times in ways that we can't predict, ways that we cannot, as people looking at it and data scientists trying to analyze it, can't say, well, this has got to be the right way. Well, in the real world, it didn't work the way the model showed. BBR, for example, was supposed to coexist very nicely with Reno. It doesn't. It completely dominates the path. That's just because in the real world, packets don't behave exactly how some of the simulated models do. But by using an algorithm that's feeding back continuously, we think we can get there. So, just to let you know, HTTP 3 has been officially defined, and that encapsulates HTTP over QUIC, so the ability to use QUIC to transfer HTTP content. So this is an easy projection. This one's the simple one. So 3 years ago, when HTTP 2 was released, today about a third of websites are using it. So I'm going to make the same prediction forward. In 3 years' time, a third of the websites are going to be using HTTP 3. I think that'll actually be higher because I think a lot of people are already using it. It's just not in the standardized form. So I think that number will probably go higher by 2022. So 2 things. Per-session protocol optimization will become the norm, hopefully using some very clever algorithms behind the scenes. And HTTP 3 will be used for the majority of media traffic because increasing throughput is something that we need for media traffic. We have the most to gain from using that. Let's talk about codecs. I quite like this slide, which is we live in an H.264 world where there really isn't a lot of other things. Why? Because it was there when we started doing OTT. All of our catalogs are encoded in it. It worked well for the way the world was working at the time. Why? 98% of devices support H.264. We don't have to worry about it. It's got global coverage. HEVC, on the other hand, is used for the biggest. It's there in the distance. It's used for those 4K events. It's used to feed devices that have hardware in them that can support it. AV1, AVP9 is used for user-generated and for other stuff, so it's kind of in the distance there. But in terms of OTT, broadcast video applications, H.264 dominates the world. Part of the reason HEVC is not as ubiquitous, well, the regulatory world, the whole patent pool and licensing problems, which I'm going to get to in a second. But it's there because when we have to go to a 4K or we have to go to a format we just can't get the quality or the bits with HEVC, we're going to move to that newer codec. So by 2022, I think the landscape will have changed. I think we will have a more verdant valley. We won't just have this desert of H.264. H.264 is absolutely still going to be there. We're not going to go back and transcode all of this old content. But there will be more HEVC hills. There will be AV1 hills. There will be EVC hills, and there will be VVC hills. So I think we'll live in a much more multi-codec world, whereas in OTT at least, we haven't had to embrace that, unlike what we've had to do in the broadcast industry in the past. I think our reckoning is coming there. How are we going to handle all these codecs? Again, cloud transcode has got very ubiquitous and very, very inexpensive. I think with edge servers being able to give us feedback about who's consuming what data, and then applying business logic rules that say, if I have a device that needs lower bandwidths, I can spin up and create those in real time and put them into my storage when it makes business sense to do it. Also, as other devices appear on the network, which can have a better experience, I will then go back and get my MES, and I will make higher quality experiences to feed those devices. As devices, say laptops, which can support, say, AV1 appear, and it makes business sense for me to pay for the storage and the transcode versus the delivery, I will spin up other renditions in other formats which look better and feed those devices in a nicer way. When a big smart TV that can do a really nice HDR 4K experience, I'm going to spin up higher bit rates in those higher formats when it makes business sense to do that. I think this is the way that we're going to handle multi-codecs in the future. And as popularity of content drops off, and as content falls out of the catalog, we will make trim rules, and we will automatically manage the cache and manage the origin, so we're not storing bits forever and ever, as we tend to do today, these giant libraries in every possible format that we may possibly need. I think it will be much more dynamic. So let's talk about VVC. This is from the BBC's research paper. This is comparing the reference HEVC encoder, HM, to GEM, which is the reference VVC encoder today. What we're seeing is about a 30% improvement, which is about where we expect to be this far into the life cycle of a new codec. We're also seeing, as you can see, you get an improvement of AV1 versus the reference encoder today. So this is where we are with VVC. VVC is the natural successor to HEVC in the MPEG codec line. I've been through 3 of these now. When I started, I was building a refrigerator-sized MPEG-2 encoder for NTT in the UK. And now we're down to little tiny things that can compress this stuff into infinitesimal pieces. So this is about where we are in the life cycle. But what we're concerned about is maybe not the technology so much as where we got to. What HEVC has been somewhat undone by is just the patent pool confusion. And while we're kind of sorting through that, it's still proved quite a quagmire for a long time. So there are a couple of initiatives going on that I want to mention here. One is the Media Coding Industry Forum, which is a group formed with a lot of the usual suspects to basically try and save VVC from the same fate as HEVC. So trying to head this off the pass. They had an initial meeting at IBC. There is another one planned for June, I believe. And we hope that they can come together and really try and get VVC to move forward in the right direction. In the meantime, MPEG has tried to kind of head this off at the pass, as you were, by coming up with EVC, or the Essential Video Codec, which is not as aggressive as VVC. The intent is to be maybe halfway between, so HEVC, 25% better would be EVC, 50% better would be VVC. So EVC is designed to use any tools that don't have IP, or anything that's over 20 years old, or stuff that doesn't have royalties attached to it to start with, as the baseline. So we have a codec that's essentially royalty-free, and that everyone can use, at least at the base layer. On top of that, they want to have all of the different tools that you can turn on and off in the codec be switches and independently clicked in and out. Therefore, if the licensing doesn't work out on one component, or you can just simply turn off that tool in these higher layers. And that they're really trying to start from a focus on the legal side of the codec as they put the tools in, versus building a really awesome codec and then everyone going, that's mine, that's mine, that's mine. And we got ourselves into a big mess. So 2 things going on. One is VVC, and then the media, the MCIF trying to basically shepherd the licensing through so that we get to fair and reasonable terms. And then we have EVC, which is trying to build a codec, which will be the kind of standard replacement for H.264 going forward, which is kind of an open source, essentially, not an open source, but a royalty-free codec at the baseline with easily and simple tools added on top of it. So kind of 2 different paths going on there. So on the other side of the house, in the open source world, we have AV1, which has been going really, really well. Recent releases I want to highlight here is the DAV1D, or David. I'm not sure how you're supposed to pronounce it. I haven't spoken to somebody of an authority that's told me correctly. Maybe somebody can fill me in here. But this is a runtime optimized version of the decoder. Much smaller memory, much easier to download. You can go and download this and test it. It looks really good. Decoders always need encoders. So there is a new encoder for AV1, again, open source. This is faster than the reference library. This is the RAV1E, and there are some nice curvy charts of vSim scores showing that blue is better than green and vice versa, and that this is now fitting within a reasonable CPU footprint. So again, lots of work going on the AV1 side as well as on the MPEG side. What does all of that mean? I believe that with all of these activities going on, multi-codec will become the norm. I believe there is, in the future, we will have AV1, HEVC, and EVC. VVC is still to be determined. And the HEVC, AVC, or H.264 will still be there for legacy support. So, bandwidth. How do we buy bandwidth? These are all recent ads, by the way. You buy it per gigabit, or except an example up there of 760 kilobits. I'm guessing that's an AT&T service somewhere in the Midwest. I'm not sure. Who would pay $40 a month for 760 kilobits these days? Probably my mother. But the point is you buy bandwidth by the peak speed that you can achieve on your link. You buy it by the peak. You don't buy it by volume. Bandwidth pricing, as you know, keeps going cheaper as we get lasers that can now put, almost terabits of data onto a single piece of light, and we can combine all these things together. Bandwidth pricing keeps going down. And the consumers aren't buying it per gigabyte. The CDNs don't buy it per gigabyte. And the ISPs don't buy it per gigabyte. In fact, the only people in the media ecosystem who still buy data per gigabyte are you. So here is my next prediction, which is this is going to change, where CDN pricing will shift to non-volumetric models, per subscriber, per minute, or peak capacity. This is already happening. This is not new. This is just following the trend of the data. So, peer-to-peer kind of has a bad connotation in the world. We've tried to rename it so people don't think of it as peer-to-peer, like edge-assisted delivery, or peer-assisted delivery, or simulated multicast, or some other term that doesn't use the word peer-to-peer, or our friends that have kind of spoiled that whole business by coming up with these great file-sharing schemes and, of course, all these legal problems. But peer-to-peer gets a bad rap just by its name. But as a technology, and I do feel like I'm sounding like a broken record because I think I've given this speech for the last 5 years, peer-to-peer is a very powerful tool that we need in our arsenal. Why? It scales proportionally to consumption. When you have a large event, today we hit a peak event of, say, 10 million concurrents. 10 million concurrents is a lot for OTT. But that's not a lot for a big sporting event like the Super Bowl, which is 120 million concurrents. How do we get from 10 to 100 million? You need something that's going to scale even further than what we can do with edge servers today. So P2P scales proportionally with consumption. It's very low COGS because we're pushing out the tech right to the edge and we're sharing that all of that technology. It keeps the traffic on net. If I'm a carrier or an ISP who has an access network, my access network probably has a lot more bandwidth than my regional or my core network. So between access nodes, there's a lot of bandwidth between those edge, and it keeps the traffic on net. It's not going to go up and down through transit. So again, that fits in the right model. Multi-source, and the way we've built models is we would have typically eight clients in a rotation, 6 active, and then 2 which are being swapped in and out. You have 8 sources for any piece of data. There's 8-way redundancy, at least 6-way redundancy. Sometimes we don't even do primary and backup, but 8-way redundancy, this thing is incredibly fault tolerant and robust. And that's built in because you're trying to source the bits from the nearest partner that has the best RTT to you or has the best delivery profile or has the best connection available to you at that moment. So it's incredibly fault tolerant and robust. What's wrong with PTP? This is the big one for me. It consumes the end user's compute and bandwidth. So if I'm using a service which has a P2P component and suddenly I'm sat there and my fans fire up on my laptop, I'm like, time for Wireshark. Let's see what's going on. People spot that. People figure out what's going on. So unless you tell them you're going to do it or include them in the question, you get these, they call it the 1-5. There's 1% of people who know what's going on who complain to 5% of people on Reddit, and then 5% of people on Reddit then complain to the carrier or the operator saying, hey, how dare you use my laptop for this? Or how dare you use my bandwidth? It's using the ISP's connectivities and routers. So you are taxing their access network, and they have to be prepared for that, and they have to have some level of control over how that happens, or how far those nodes can spread and how far that traffic can be routed. It does still require reliable seeds. It's better if you have a coordinated signaling server system to actually set up these seeds and actually allocate these, because peer-to-peer works very well kind of on its own, but if you have bad actors or you have unreliable seeds in the network, it can cause like local problems in the peer-to-peer network. And content integrity is critical. You have to be able to rely on these things because it's very easy to attack these things if you know what you're doing and you can get yourself into the right position to do that. So how can we fix this? Well, come up with a way to compensate the end users. Say, hey, sign up for this service. If you enable this, by the way, here's the T's and C's. We will give you access to additional content. We will give you a discount on your something. People will they will give up a lot of things for a very simple token. If you just say, hey, you get access to this extra library, or you get to see the highest tier. You get to see the HDR experience if you enable this feature, if you allow us to use your compute and your bandwidth to do this. Part of what we've built into at least some of the models we built is the ability for the ISPs to actually control how the P2P network scales, how many nodes can be in an access group, how big those groups can be, where they can be. So you can actually shape it to actually fit the shape and the style of their access networks and give them the ability to control that and decide how much monetization they're going to try and pull out of that or how they're going to try and share that burden into their networks. As a content distributor, you're going to be saving so many bits on your delivery. Share the wealth or bring them into the fold and make them part of the equation. Reliable seeds can be delivered by networks that also handle a lot of certificates, security keys, and other things out there. So CDNs are very good at that today. Integrate the seed delivery into the CDNs directly. And for content integrity, we have all of the tools today for zero trust segmentation to authenticate clients with each other and make sure that the person generating and sending bits of the fragments to a peer are who they say they are and are providing reliable fragments and that they are the same ones that everyone else was sharing. So this is all completely doable. So again, did make this prediction about 3 years ago. We'll make this prediction again. Believing it to be true and going to happen is that PTP will be an integral part of how we deliver content, especially for very large-scale events. I think it's the way that we get ourselves that next order of magnitude growth. So with that, these are my 12 projections for the next 3 to 5 years. I thank you for your time and attention. And if you have any questions, I will try and answer them in the time I have remaining before Eric comes and gets me off the stage. Thank you very much.
Right, folks, let's have some questions. And who's going to be first to get their hand in the air? I might put someone on the spot otherwise. It's that morning thing. Great presentation, Peter. Okay, well, I'll start the ball rolling. On your last point about P2P, watch out for feedback on the microphone there. Yeah. On your last point about P2P, do you not think that deploying IP, some of you are going to laugh when I ask this, I know this. Do you not think that deploying native IP multicast would be an equal challenge and in the long run more effective?
I agree. I think deploying multicast is also a worthy path to follow, and I think we've got several different options in front of us, and we should be pursuing all of them with vigor. So I agree that it would be a way of doing it, and I think there is a longer-term benefit to that, and it certainly avoids some of the problems, but I think both have a role to play.
Okay, cool. Come on, guys. Let's have some questions in. You're looking for coffee, aren't you?
They are looking for coffee.
Well, I'm not going to let you go yet. I'm going to keep asking questions. So you talked about the most content being delivered from the edge.
Yes.
So one of the problems we had with the session protocols, which solved a lot of the latency challenges 20 years ago, 15 years ago, and we're sort of revisiting those problems in some ways in the post-HTTP world, was that deploying all these different varied types of protocols with their specific servers deep into CDN networks was a costly exercise, a complex exercise. Yes. But as edge computing comes in more and more, and some CDNs at least are starting to offer the ability to effectively host fog architecture and deep cloud architecture.
Fog. Fog computing.
Fog computing.
I laughed when that was first. I remember Cisco saying that about 5 years ago. I went, fog, come on.
Oh, yeah. No, I think
but it makes sense.
Especially in the MEC world, it's been spoken about a lot, I think, and so on. So as you start to see people being able to run their choice of application deep on the edge of someone else's network, one way of solving some of these latency problems would be to go and boot up a few old Adobe Flash servers and run them at the deep edges of your fog account in some of these architectures.
You certainly could do that, but we've definitely seen a trend for, what didn't work with Flash was just trying to traverse NATs and firewalls. Yeah. Anything that wouldn't...
Maybe the wrong example, but...
No, you're right, but I think especially when you look at gaming, having, essentially we're going to have computers sat at the edge which we don't own, so it's going to be somebody else's computer very close to us, as opposed to somebody else's computer somewhere where we don't know where it is. So I think the choices, especially in the protocol selection, they were all TCP protocols. They were just different congestion control algorithms, which some of them are really good, some of them are very stable, some of them are very fast. Some have different characteristics that make them very aggressive. What I'm saying is that we will have the ability, at least on open, shared links where there's a bunch of things going on, to pick the right protocol so it achieves what the application wants, but it doesn't destroy the link for the other actors on that link. So. That's fairly within one protocol family, I guess, or at least that link. But to your point about edge computing or fog computing, that there will be a lot more interesting experiments going on there and a lot more ability to use things which we wouldn't have been able to do where we had to go back through transit.
A bit more customized or tailored, Okay, brilliant. Last window for a question from the floor. Great. Oh, we've got 2 hands up now. That's what we needed. Eric, do you want to run to them? Yeah.
Hello.
Hi.
So is Akamai seeing pricing on CDN that's non-volumetric right now?
We are, yes.
Can you share a little bit more about
I would refer you to one of our account representatives or something like that. I don't normally wear a suit. This is kind of a blind. Normally, my wardrobe is like 7 T-shirts and 2 pairs of jeans, and I'm usually stuck in a data center under a rack somewhere. So we are seeing those models, but I couldn't talk to specifics about accounts and stuff or how many there are.
There was another question at the front here.
Yeah.
Good morning. Thank you.
Good morning.
Great presentation.
Thank you.
I've been playing with low latency for about 6 months with AWS, and one of the things we've run into is there's a lot of niche long tail live content that, that we're playing with low latency. And moving it to the next level to, major sporting and stuff like that, you start throwing DRM in it, ad services, and all these other things. That's the end of low latency as we know it. You got any thoughts on that, the trade-offs?
Yeah. So what I showed you there was, this is standard CMAF chunks. To make ad insertion work, typically, because we've had ABR in the way and everyone's been sat at like 30 seconds to 45 seconds, the fact that ad insertion was taking at least a segment plus a segment or two, we probably had like 10 to 12 seconds of decision time to play with, to spin up and make all these new manifests. So the way that the ad buying system was set up was very much on demand. So it would say, okay, here's an ad break, right, go off, put it out. Now we're using header bidding, so we're trying to pre-cache from that. Maybe we're going out to different markets, different waterfall models. We're trying to get decisions back and trying to get the best CPM for that avail. What's going to have to happen with low latency is like what we did with other systems where we had to have a pre-roll, so we had to have the signaling get there ahead of the actual ad break. So in sports, we typically have, it's 5 seconds of the button press or whatever was the pre-roll. I used to build cable legacy ad systems, and I still remember why we had pre-roll, because it was how long it took for the tapes to start spinning. So I am older than I look. Almost, no, not a grandfather yet. But so I think we're going to go to a model where you're either going to have pre-cache decisions, and we're going to have to change the way that ad buying systems have, essentially the idea of giving a head request, which is like, hey, I don't have the full request yet, but if I was to, what would you give me right now? And then maybe that's a cache decision that we will have locked in, or maybe there's a signaling mechanism where we're pre-filling ads so that when we're there, we're ready to do the splice. Because the actual switch is very quick. The only latency we're introducing is typically the time it takes off for the VAST request to go off, to go through the myriad of different redirects and bidding markets to actually come back with a valid response and then get creative to flow back. If that request is done ahead of time, or at least is done with sufficient pre-roll, I think we can bring the latency in. Today I'm seeing, maybe 2 to 3 seconds is what you have to add with low latency and ad insertion. That's doable. We'd want to get that down so we can keep the low latency really tight. Question?
Yeah, thanks. So I have Sprint as my cell phone provider, and it's like the worst network. So it's terrible. But the reason why I bought into it was they had this awesome special, and so you could get like unlimited connectivity for $5 a month for the first 18 months, and I was like, hey, this is a deal, yo. This is a deal. So my question is, if the CDN pricing is moving away from per gigabytes that traditionally come with SLAs around that type of a buying pattern, will we see the SLAs that companies like Akamai provide switching over to metrics like end user QoE for the first time? Tell me yes.
That's a really good question. The intent was not to, as far as I'm aware, again, and I put back on my engineer clothes rather than my looking like a business person here. The intent is the SLAs would say the same. It was just we changed the buying model to be a per subscriber or per something other than volumetric, which has been the traditional.
We're not buying volume anymore, but
no.
the SLAs will still be.
I will refer you to my business director over the corner on the exact details of that. We're just seeing the model shift that way, where people are asking for it to be that way. So, yeah. Yes, question in the center.
Yeah. So we'll take this one more, and then I will have.
No, we will let you have coffee.
Yes. With respect to bit rates, I believe you said 4K was 16 megabits
16
per second
megabits is
coded, right?
Correct, yeah.
Raw bit rate, what would that be?
The original bit rate of 4K coming in from a camera is 12 gigabits per second for 60 frames per second.
Okay. Now what about 8K? What's the coded bit rate?
8K is multiplied by 4, so it's 48 gigabits for 10-bit, which you probably want to go to a higher format, and depending, depends on your chroma format and your bit depth.
Okay, good. Well, quickly, you said transit is going to disappear. No,
I didn't say transit.
Almost.
I said content, the big content companies are going around transit
By direct connect, right?
By direct connecting to servers that they host at ISPs, and they're building these overlay networks. If you look at who's buying submarine cables between countries, it is not carriers.
Yeah,
It's Facebook.
Facebook,
Yeah.
Google. Okay.
And that's an interesting thing that we should all be aware of.
Well, Peter, you've set the scene for the day really well. I think I'd like a round of applause for Peter, because that was a great opening.